IBESS, Atmospheric Systems and Pollution Management Part 1, will provide an introduction to the atmosphere, its composition, and structure. Part 2 will explain the greenhouse effect, while Parts 3, 4, 5, 6, 7, and 8 will focus on pollution, pollution management, and specific types of atmospheric pollution. This unit will not examine climate change, which is arguably the biggest societal insult on our atmosphere. Climate change is a unit unto itself, the next unit. The significant ideas are the atmosphere is a dynamic system that is essential to life on Earth, and secondly, the behavior, structure, and composition of the atmosphere influence variations in all ecosystems. Here is the outline of all the available movies in the unit called Atmospheric Systems and Pollution Management. Use this outline to find the movie you need for review. This movie is focused here, Introduction to the Atmospheric System. The atmosphere is an extremely thin layer of gases that surrounds the Earth's surface, held close to the Earth by gravity. The layer is so thin that if you could drive through it from the Earth's surface to the top edge of the atmosphere, you could do so in less than an hour without breaking the speed limit. The mixture of gases known as our atmosphere is a dynamic system with storages and flows, inputs and outputs, and the atmosphere is critical to life on Earth. The atmosphere is a mixture of gases. Now's the time to take some notes. The air is a mixture of nitrogen, N2, oxygen, O2, with smaller amounts of carbon dioxide, CO2, ozone, O3, argon, water vapor, and other trace gases. The atmosphere is a mixture of molecules, but not all of those molecules are gas. Liquid water, as we can see in the clouds of this image, would be included as part of our atmosphere. Here is the relevant IB syllabus statement. The atmosphere is a mixture of nitrogen and oxygen with smaller amounts of carbon dioxide, ozone, argon, water vapor, and other trace gases. Water vapor is gaseous water, invisible to the eye. Liquid water in the atmosphere is visible to the eye, such as clouds. Spend some time with this slide. The atmosphere is mostly nitrogen at 78+% and oxygen at nearly 21%. Keep this in mind. Water vapor, carbon dioxide, and ozone represent just fractions of a percent of the entire gaseous mixture. The atmosphere is predominantly a mixture of nitrogen, N2, and oxygen, O2, with smaller amounts of carbon dioxide, ozone, argon, water vapor, and other trace gases. Trace gases include argon, helium, and neon, but there are also trace levels of sulfur dioxide, nitrogen oxides, and methane. Now, these substances become important in our discussion of atmospheric pollution. Take some notes now. Don't miss this slide because the term trace appears to indicate no relevance. That's not the case. And the concentration of many of the atmospheric gases, carbon dioxide, methane, nitrogen oxides, and CFCs have increased over time. In these graphs, you can clearly imagine the atmosphere as a storage with inputs. Human activities have impacted the composition of the atmosphere by altering the inputs and outputs of these gases. And the changes in the concentration of these gases has had an effect on ecosystems. In this graph, you can see the overall increase in carbon dioxide concentration in the atmosphere since 1960. Human activities, such as burning fossil fuels and deforestation, have caused this increase in the concentration of carbon dioxide in the atmosphere. Solar energy is an energy input to our atmosphere, but as we burn fossil fuels, carbon dioxide is also an input, a material or matter input to the atmospheric storage. Remember that some of the trace gases, sulfur dioxide, nitrogen oxides, and ozone, are also inputs to the atmospheric system due to human activities. Here is the relevant IB syllabus statement. The atmosphere is a dynamic system with inputs, outputs, flows, and storages. And human activities impact the atmospheric composition through altering the inputs and outputs of the system. Take note of the human activities, such as fossil fuel combustion. The Earth's atmosphere is a dynamic system with inputs and outputs. Take some notes. Water flows into the atmosphere through evaporation. Water flows out of the atmosphere during precipitation. Carbon dioxide flows out of the atmosphere during photosynthesis. Carbon dioxide flows in during respiration. Carbon dioxide flows in when societies combust fossil fuel. Nitrogen gas, N2, flows out when we industrially manufacture fertilizer. Sulfur dioxides and nitrogen oxides flow in when we combust fossil fuels and use fertilizers. CFCs flow in when we use air conditioners, refrigerants, solvents, and manufacture styrofoam. Ozone breaks down, flows out when it comes into contact with CFCs. Ozone has the capacity to regenerate, but flow rates are slow. Stratospheric ozone is a renewable, non-living resource. The rate at which these flows occur is the key to understanding whether or not the atmospheric system is in equilibrium with any of these substances. Here, I've labeled the processes that create the flows of the inputs and outputs that I mentioned in the last slide. These flows involve changes of state and chemical change, transformation, photosynthesis, respiration, combustion of fossil fuels are all chemical reactions, transformations. CFCs are released by people at the Earth's surface and are transferred to the stratosphere. Ozone breakdown and formation are reactions, transformations. Stop the movie now and take some notes. Remember, solar energy is an energy input to the Earth's atmosphere. And heat is an energy output, leaving the Earth's atmosphere for the universe. And the atmosphere is a dynamic system with inputs, outputs, flows, and storages that has undergone changes throughout geological time. This graph displays changes in the Earth's temperature and carbon dioxide concentration over the last 160,000 years. You can see the fluctuations in both temperature and carbon dioxide over time. The atmosphere is a dynamic system with inputs, outputs, flows, and storages that has undergone change throughout geologic time. Even in recent time, with the increase in carbon dioxide concentrations, temperature has followed. Here is the next IB syllabus statement. The layers of the atmosphere include the troposphere, 0 to 10 kilometers above sea level, and the stratosphere, 10 to 50 kilometers above sea level. The atmosphere has structure, and our focus will be on these two layers, the troposphere and the stratosphere. The layer of the atmosphere closest to the Earth is known as the troposphere. The second layer is the stratosphere. The third and fourth layers, not shown here, are the mesosphere and thermosphere, respectively. This will be the last mention of the meso and thermospheres. The layer of the atmosphere closest to the Earth's surface is the troposphere. The temperature of the troposphere decreases as the altitude increases. Most of the clouds that you see in the sky are in the troposphere. The troposphere layer is 10 kilometers thick from the Earth's surface to 10 kilometers above sea level. Commercial aircraft fly about 10 kilometers high at the boundary of the troposphere with the stratosphere. Now the layer above the troposphere is the stratosphere. The temperature of the stratosphere increases as the altitude increases up to about 50 kilometers above sea level. Stratospheric ozone is located in the stratosphere. Once again, the troposphere is close to the Earth's surface, and the temperature of the troposphere decreases up to about 10 kilometers above sea level. The stratosphere is just above the troposphere. The temperature of the stratosphere increases from 10 kilometers up to about 50 kilometers above sea level. Here is another image of the structure of the atmosphere. Notice that the clouds are found predominantly in the troposphere. Notice commercial aircraft fly at the top of the troposphere. And then notice the location of the ozone layer in the stratosphere. In this graph, you can see the variation in ozone concentration, ozone density, through the atmosphere from sea level to the top of the stratosphere, 50 kilometers above sea level. Most of the ozone is located between 15 and 30 kilometers above sea level in the stratosphere. Here's the next IB syllabus statement. Most clouds form in the troposphere and play an important role in the albedo effect of the planet. Define the albedo effect. Albedo is defined as the proportion of the incident light or radiation that is reflected by a surface. Anything that reflects the entirety of incoming solar energy has an albedo of 1. Snow, ice, and the tops of clouds reflects incoming solar energy with an albedo that approaches 1. In this image, we can see high albedo as light reflects off of snow, ice, or the tops of clouds, or the surface of water. The reflection of solar energy off of white surfaces serves to keep the Earth cool as less solar energy is absorbed. The reflection of light from white surfaces, the tops of clouds or ice, means less solar energy is absorbed by the Earth. This serves to keep the Earth cool. Now, if clouds were to disappear or the ice were to melt, more solar energy would be absorbed, heating the Earth. With more heating, there would be more melting. This is a positive feedback loop. On the other hand, if the Earth's atmosphere warms, as the climate change scenario suggests, more water would evaporate, resulting in more water vapor in the atmosphere, and this might result in more cloud cover, increasing albedo. This would reduce the solar energy absorbed, serving to cool the Earth. This is a negative feedback loop. Once again, clouds have high albedo, serving to reflect solar energy back out to the universe. Clouds would reduce the absorption of solar radiation at the Earth's surface. This would serve to cool the Earth. Ice, snow, and the tops of clouds reflect solar energy, serving to reduce the amount of solar energy absorbed at the Earth's surface. This tends to keep the Earth cooler. Of all the incoming solar energy, of all of it, about 50% arrives at the Earth's surface to be absorbed by the Earth's surface. This would include photosynthesis as well as the heating of sands or ocean water. You can see that approximately 30% of incoming solar energy is reflected by the surfaces with high albedo, snow, ice, and cloud tops. 20% of the incoming solar energy is absorbed by the gases in the atmosphere. Both the reflection and the absorption seen in this image become important parts of the discussion in the regulation of the Earth's average temperature, which is the subject of the next movie and the subject of the climate change unit. Work to make the connections between what I introduce here and what gets covered later in the course. So this IB syllabus statement is one that is only introduced here but needs further coverage in the unit on climate change. Discuss the role of the albedo effect from clouds in regulating the global average temperature. The presence of clouds in the troposphere would serve to regulate global average temperature in two ways. Clouds can absorb heat from the Earth's surface, serving to warm the Earth, or clouds might reflect light with their high albedo, serving to cool the Earth. Now, there are two feedback loops that could occur here. Clouds form as water vapor condenses. Water vapor in the atmosphere results from evaporation at the Earth's surface. An increase in the Earth's temperature would result in more evaporation, thus more water vapor in the atmosphere, and that might result in more clouds. Now, more clouds could result in more reflection of solar energy, serving to cool the Earth. This is a negative feedback loop, but more water vapor and clouds in the atmosphere might absorb the Earth's heat warming the Earth, and this is a positive feedback loop. Now keep in mind that snow and ice and cloud tops reflect solar energy, but liquid water does not reflect, but instead absorbs solar energy. As the ice caps melt, less solar energy is reflected. More light will be absorbed. Thus, the Earth warms further, melting more ice, further reducing the reflection, further increasing the absorption of solar energy. This is a positive feedback loop. The last IB syllabus statement of the movie is, most reactions connected to living things occur in the inner layers of the atmosphere, the troposphere and the stratosphere. The atmosphere is essential to life on Earth. Living things require the carbon dioxide for photosynthesis. Living things require water from the hydrologic cycle. And living things require the stratospheric ozone layer to remove harmful UV radiation before it reaches the Earth's surface. The troposphere and the stratosphere are the layers of the atmosphere where most reactions connected to living things occur. Reactions connected to living things occur in the inner layers of the atmosphere, the troposphere, and the stratosphere. Humans impact the natural balance of photosynthesis and respiration through deforestation, which adds carbon dioxide to the troposphere. Humans increase the concentration of carbon dioxide in the troposphere when we burn fossil fuels. Humans add sulfur dioxides and nitrogen oxides to the atmosphere when we burn fossil fuel, and nitrogen oxides when we spread fertilizers on farm fields. Humans add CFCs to the atmosphere when we use air conditioners, refrigerants, and solvents, and manufacture styrofoam products. CFCs transfer from the troposphere to the stratosphere, where they accelerate left to right the breakdown of stratospheric ozone. As you consider the troposphere and stratosphere, keep in mind the structure of the atmosphere. The temperature decreases with altitude in the troposphere, and it's within the troposphere where the clouds are found. Temperature increases with altitude in the stratosphere, and it's within the stratosphere that the important and beneficial ozone layer is found. So let me come full circle with IB syllabus statements that I've presented previously in this movie. Human activities impact the atmospheric composition by altering the inputs and outputs of the system. Changes in the concentration of atmospheric gases, such as ozone, carbon dioxide, and water vapor, have significant effects on ecosystems. The concentration of many of the atmospheric gases, carbon dioxide, methane, nitrous oxide, and CFCs, have increased over time. Human activities have impacted the composition of the atmosphere by altering the inputs and outputs of these gases, and changes in the concentration of these gases has had an effect on ecosystems. In this graph, you can see the overall increase in carbon dioxide concentration over time over the last 50 years. Human activities such as the burning of fossil fuels and deforestation have caused this recent and relatively dramatic increase in the concentration of carbon dioxide in the atmosphere. The increase in carbon dioxide that you see here will be the focus of our unit on climate change. And that brings us to the end of IB ESS, Atmospheric Systems and Pollution Management, Part 1.